today. My name is Tom White, and I'm going to be talking about building big data applications with Hadoop. So first, a little bit about me. I'm an engineer at Cloudera, and I've been working on core Hadoop for the last several years. Earlier this year, I started on a new project, which is called the CDK, which is going to form the basis of what I'm talking about today. CDK stands for Cloudera Development Kit, and its overarching aim is to make it easier to build applications running on Hadoop. I'm also involved at Apache, and I also wrote Hadoop, the Definitive Guide, published by O'Reilly. I'm going to start with a very simple question. What is Hadoop? I'd like to do a quick poll of the audience, if that's okay. If you've heard of Hadoop, please raise your hand. So that's pretty much everybody. If you've used Hadoop in any form, in testing or just playing around with it, please raise your hand. That's less people, probably a third or so. And if you use Hadoop in production, please raise your hand. That's even less, obviously. I'd say about 10%. So quite a small number using Hadoop in production, but most people have at least heard of it or tried it out in some way. So to answer the question, Apache Hadoop is an open source system to reliably store and process large volumes of data using commodity hardware. And to compress that definition even more, I would say something like it's distributed infrastructure for big data. And really the thing I would really focus on is that it's to reliably store. So the thing that it does really well, apart from the big data aspect, is the way it handles failures. If any of the nodes in the cluster fail, then the data stored in the system obviously is safe. You won't lose any data, but equally, if you're processing data at that point, then the program that's running, from the user's point of view, will not notice. So it's transparent to failure from the application developer's point of view. If I'd asked that question a few years ago, I think a lot of people would have said, oh, Hadoop is two things. It's HDFS and MapReduce. HDFS is the Hadoop distributed file system, and MapReduce is the processing engine that works alongside HDFS. In fact, they were designed to work together. HDFS is very efficient at storing large files that are written in a streaming manner. And MapReduce does exactly that. It reads files in a streaming manner, and then it will write new large files to the file system. So it's really a batch processing system. You have a large amount of data in there, and then you'll transform that with MapReduce into a new data set. So think of something like a search index. This is where it was born at Google, of course. And you're basically, each time you process that, you're processing the whole data set and transforming it into something new. So the emphasis a few years ago was certainly on batch processing, but now there's a slightly different picture. I think Hadoop has developed in the last few years, and it's changed what it can do. And I just wanted to draw attention to that in this diagram. This is a diagram of a Hadoop stack. It's also known as a Hadoop distribution. There are several vendors that produce Hadoop distributions these days. Cloudera is one of those. This is what our stack looks like. And in fact, the layers that I have in this diagram are a simplification. There's more components in the system that I'm just not showing on this diagram. There's more detail. For example, the storage layer would include HDFS, but in addition to HDFS, it would include HBase, and then the other layers, like resource management, would include other components. You may have heard recently that Hadoop 2 became generally available. It's now been declared stable, and one of the big changes in Hadoop 2 is the addition of a framework called Yarn, which is a resource management framework. So that would live in that layer. So all of those components are common. If you look at the top of the diagram, you can see that there are a number of engines that run on the lower layers. And the first one on the left is a batch processing engine, and that was the one I mentioned earlier with MapReduce. And a few years ago, that was the only one. It's still a very important part of the system, but there are other engines as well. The MapReduce engine, has other components in it as well, like Hive and Pig, which are components. Hive is a component for doing SQL on Hadoop, and Pig is another data flow language system. But the point is, both of those are batch processing systems, and they use MapReduce to run their jobs. Now, however, there are new engines. So we heard a lot of announcements in the last couple of years about interactive SQL that runs natively on Hadoop. Cloudera Impala is one of those systems, and it will it uses the underlying storage of HDFS, but it doesn't use MapReduce. It runs its own daemons in the cluster, and it provides faster SQL by avoiding the kind of time-consuming batch processing phase of MapReduce. Similarly, there are other engines like Interactive Search, which uses Solr running natively on Hadoop. There are machine learning engines. There are in-memory, not on this diagram, there are in-memory engines which load datasets into memory. Spark is an example of one of those. So I think the Hadoop landscape has changed a lot in the last few years and become much more flexible and supports many more different workload styles. It's not just batch anymore. It's all of these different workload engines. I mentioned that the diagram had lots of components. I'm going to talk about some of those components in this talk, and I'm just going to quickly go through some of their names and what they do with one-line definitions. So this is a kind of cheat sheet for the talk. So just to go through them, Apache Avro is a cross-language data serialization library. If you've come across something like Apache Thrift or Google's protocol buffers, it's a similar system. The reason that it's very popular in the Hadoop world is that it works very well across the Hadoop stack. Apache Hive is a data warehouse and SQL engine. I just mentioned that as a batch processing component in the Hadoop stack. hCatalog is a part of Hive. It's actually the metadata storage system in Hive. So you can think of that as storing the table definitions in a relational database. Insofar as Hive is like a relational database, that's where the tables are stored. Apache Flume is a streaming log capture and delivery system. And the typical use case is a collection of, say you had a collection of web servers that are generating web logs, and you want to capture those web logs and store them in HDFS for analysis, then Flume is a good system for achieving that. Apache Uzi is a workflow scheduler system. You can think of it as cron for Hadoop. You can define workflows, and workflows are typically a directed acyclic graph of actions like MapReduce or Pig jobs that link together, and you can run those on the cluster. According to particular schedules, you can repeat them and run them at certain times. Apache Crunch. Now, you've probably heard of MapReduce and its Java API. Apache Crunch is a higher-level API for writing data pipelines. It's like cascading, which is another very popular higher-level API for writing programs that run on Hadoop. And Parquet, that's a column-oriented storage format for nested data. This is a relatively new project, and it's a project that was started by Twitter and Cloudera, and it's an open source project with lots of contributors, but it's a new storage format for column-oriented nested data. And Impala, which I mentioned a moment ago, is interactive SQL on Hadoop. So I mentioned that we started this project called the CDK for making it easier to develop applications, and it was born of experience with customers and users of Hadoop who had certain pain points when they were using Hadoop. So I'm just going to go through a few of the pain points that we've seen over the years at Cloudera, but just also in the community. One of the problems, I suppose, is the fact that the platform has grown so quickly that there are lots of different components in it, and knowing which components to use and how they work together is certainly one of those pain points. The one that users often meet first, though, is in choosing a file format. A common use case is they have a lot of data in some format and they want to analyze it in some way. And the question is, can I analyze my gzip compressed JSON using Hadoop? And the answer is yes, because Hadoop's very flexible. However, there are kind of constraints on what you can do and which parts of the stack support which file formats. And so it's actually quite a complicated question. In principle, it does support all of those, but which is the best practice? That's the real question that the users are asking. I won't answer that now. We'll come back to that. A kind of related point is a data model. When you're doing analysis, it's possible to treat everything as text and as strings, but that kind of becomes a problem as things get bigger, as you get more data sets, as you get more complex pipelines. You need to really have a data model where your fields are typed, and the question then becomes, how do I define that? In the relational world, it's clear you use a schema, and certainly Hadoop has the concept of schemas as well. But in Hadoop, schemas are slightly different. There's this phrase called schema on read versus schema on write. Relational databases have what can be called schema on write, because you define the schema for a database and then you load your data, and the database will ensure that the data adheres to that schema when you load it into the database. In Hadoop, however, HDFS is a file system and Hive builds on that as a file system. So you can load your files in, and because that load is simply a copy or a move operation, it won't check the schema against the contents of each file as you load those in. However, it does do checking at read time, so when you're issuing a query, it will do that checking. So that's something to bear in mind when you're using this system. It does offer some advantages. The way it handles Schema Evolution is quite flexible because of the way it does this. And the importance of schemas was brought home by this paper, actually. It's called Scaling Big Data Mining Infrastructure, the Twitter Experience. And it was written by two people who work at Twitter, Jimmy Lin and Dimitri Rayaboy. And what they did was kind of describe how their representation of data and their storage formats evolved over time. They started out with JSON, actually. And they found that they had lots of data sets, and they were doing lots of analysis on them, obviously, and they wanted to combine them often, and so they tied things together using user ID field. And they actually found 5 different variants of the user ID field in their data sets at Twitter. And if you think about it, because it was stored in JSON, it was stored in JSON, they didn't have a schema. They relied on the fact that JSON was self-describing, which meant if they wanted to find what the fields for a particular file were, they had to actually read the data from the file rather than consult any external schema, which obviously has caused this problem. And here's a tweet from someone else at Twitter called Bill Graham, and he kind of recorded the time when he found his first, what he called camel_snake with a capital S in the code base, which is a combination that I hadn't seen before. So schemas are important, but they don't really solve this problem. They just make it easier to find, I would say. If you've got a set of schemas in a database, you can look at the schemas for consistency rather than having to open all the files to see what's actually in them. And the last kind of pain point that I'm going to mention now is the layout on disk. Hadoop kind of forces you to consider where you're going to put your files. It's a file system, as I said, and most data that you're ingesting will be time-based in some way. So you're kind of forced to come up with a layout on the file system, and you have to ask this question, which one's best? And it turns out that some of these work better with other parts of the Hadoop stack than others, and you kind of have to know that. So the pattern that's emerging here is that Hadoop is very flexible. It's a kind of general purpose system. It's open source, so people can write plugins and they can make their data sets work and their formats work. You can write input formats for your own proprietary format if you like. However, it does force you to deal with these low-level concepts, which adds this extra complexity and makes you, as a developer, write code that you really shouldn't have to write. I mean, if you're using Oracle, you probably don't worry too much about its on-disk representation of data. You probably don't think too much about the way it compresses data or partitions data. So really, it should be the same in Hadoop. You shouldn't, as an application developer, have to think about these things and reinvent the wheel all the time. So communities and companies learn over time how to deal with these issues, and certain best practices evolve. So here are a few that I know about and that I've written down. So the data model problem is use a schema, and we recommend using Avro schemas. They're supported across the whole Hadoop stack, and they're very flexible. So you can typically convert Avro schemas into database schemas as well, and we'll look at that when I get to the code in a moment. Use Avro data files for row-oriented data. Avro data files are very efficient. They were designed to work with Hadoop. For example, they work very well with MapReduce. They're very compact. They have a binary representation. They're compressible, so they kind of tick all of those boxes. For column-oriented data, use Parquet, and the reason you would want to use column-oriented data is because you have a lot of columns, and your queries are only querying a few of those columns. So column databases are very old now and use that optimization. So that's completely doable in Hadoop as well. So you can choose which format to use according to your access patterns. With regard to the file layout, there's a Hive convention that is a good idea to adopt. So it's the table name followed by the partitions. Use a library like Crunch or Cascading for batch analysis. We kind of tend to avoid recommending using raw MapReduce unless you've got a very special case. And use Impala for interactive ad hoc analysis. That's a great tool for kind of exploring a data set interactively when you've just loaded it. So those were the best practices. We wanted to do more than write those best practices down. We wanted to actually codify them as artifacts. And so what we did is we created APIs, we created tools, documentation, and examples, which exemplify all of those best practices. And the idea was that you'd be able to take these examples and use them as the basis for the use cases that you have. The examples should be easy to pick up and adapt to your own use case. So the CDK, a little bit more about it. It's actually a client-side library, so it's a set of Java jars for writing Hadoop data applications. It's not infrastructure that runs on the cluster. So anything that runs on the cluster is a part of the Hadoop stack itself. And we've actually found holes in the Hadoop stack and fixed them. So if there are kind of limitations there, we've done work at Cloudera and also in the open source communities to fill those holes over over time. But anything that's client-side will go in the CDK. And the first release was earlier this year in April, and we've done several releases there. We try and release each month. It's an open source Apache 2 license project. We really like comments and contributions. It's also designed to be very modular. And at the moment we have 3 main modules. The first one is the data module, which I'm going to talk about today. The other 2 are, there's a morphlines transformation module, which is to do with search, and there's also a Maven plugin, which we'll see some examples of today as well. So I want to look at now a typical system that you can build using the CDK. And this isn't a particularly unusual system. In fact, this is something that many of our customers want to build. It's, if I had to guess, 80% want to build something like this. In fact, this diagram doesn't even mention the word Hadoop on it. It's very general. You could build it with other technologies as well. And the idea is that it's an event capture and analysis system. And this forms the core of lots of systems, and it might feed other systems, like it might feed a machine learning system as well. This is just the kind of core part of a typical system. And the idea is that you have a web application that you've written that generates events, and you want to collect those events and store them in a raw data set, which is labeled here as event data. And then you've got some code that you write to transform that event data into a set of reports, some kind of summary reports that you can look at. And you want to do that on a periodic basis, maybe hourly, maybe more often. So if we zoom in a little bit more, we can see some of the details of the system. The web application, in this case, is a servlet-based application, and it's using log4j to append events to an event bus, which is going to be Flume. So Flume, I mentioned earlier, is a log capture system, and Flume is going to deliver those events to HDFS. The Flume agent, by the way, runs, this diagram doesn't make it clear, but it runs on the same machine as the web application. So if you have a kind of tier of web servers, then the Flume agent would typically run on those web servers, and then there would also be a tier of Flume agents running on the HDFS cluster as well. So it would that topology would ensure that it could scale to the Hadoop cluster. But the effect is that the events are delivered into HDFS and stored in the event data dataset there. And if you look at the top of the diagram, the way that the hourly reports are generated is via this Oozie process, and Oozie is this cron scheduler that I mentioned, or cron-like scheduler. It doesn't use cron. And you would define a workflow that ran every hour, and that would invoke a crunch job that would build the reports. So the crunch job does the actual transformation. And off to the side on the right, we've got Impala, which allows us to do ad hoc reporting. We can do arbitrary queries against the reporting data, or we could even query the raw event data as well. Zooming in a little bit more, I'm not sure how visible that is now. A few more components appear. We can see on the left that we're using an Avro entity as our event object. The Flume agent has a bit more structure, and it's actually sending data to various partitions in HDFS. So I mentioned partitioning in the context of Oracle earlier, and also in the context of the file system layout. The infrastructure here is aware of partitioning and does it on our behalf. So it's creating the partitions in HDFS for us. It's also registering those partitions in the Hive metastore, which is where the table definitions reside. So all of this is happening for us without us actually writing code. The other parts of the diagram are actually the same. So now I'm going to step through some code. I've got some code snippets and some explanations that I will walk through now. There are some concepts, so I'm just going to go through some definitions. A data set is a collection of entities. I talked about entities flowing through the system. The entities are the events in this example. And a dataset repository is a physical storage location for datasets. And that means, in this case, it's going to be HDFS. So we have an HDFS dataset repository, but we can equally have an HBase dataset repository. And a descriptor holds the metadata. It describes the schema and the format, which might be Parquet or Avro in this case. And then we have a writer and a reader for the dataset. And those simply do streaming writes or reads to or from the dataset, typically in a batch mode. So you would stream over large portions of the dataset. Okay, so the first step is to define the event entity, and this is very simple. We're just using a Java POJO in this case. We've defined an event with an ID, a timestamp, and a source, and those are simple fields, and we have getters and setters, and that's it, really. To actually create the events dataset, we first of all need a repository of some kind. Here we're going to use Hive as our repository, which means that the metadata will be stored in Hive, and the files will be stored by Hive, but they'll be stored on the file system in HDFS. You can have more complex URIs than that one. We have just repo:/Hive, which means Hive will take care of everything, but you can specify extra parameters to that. Next, we create a descriptor, and the descriptor has a schema, which is defined by the event POJO that I just showed you. So what the CDK will do at this point is take the event POJO and work out the fields in it and create an internal schema, which is represented by Avro, but also stored in Hive in the metastore. But it will do that for us. So we just think in terms of the Java object at this point. And once we've got a descriptor, we can use that to create a data set that we call events. Equivalently, we can use the Maven plugin to do the same thing. So we don't need to write code if we don't want to. There's a Maven tool that is invoked using CDK:create dataset, and pass in the dataset name and tell it the fully qualified Java class of the POJO, and it will create the dataset for us. And there are several different Maven commands there. You can update or delete datasets as well as create them. You can also manage applications. I'll talk a little bit about that later. Once we've created the dataset, we can peek at what it actually did, what Hive actually did, what CDK did and how it was stored in Hive. If we type describe extended events, that's like a describe table command, that's just SQL. And extended will actually print out the schema, the internal Avro schema that's being used. And if you look at it, it's actually very similar to the POJO. Its name is the name of the Java class. The namespace is the package. The type is record, which is an Avro type. And then there are three fields which correspond to the three fields, the three properties of the POJO. And the type mapping is quite straightforward as well. Avro has a fairly rich set of types which correspond closely to Java's types. So we haven't got any data in our system, so the next step is to write some data, write some events. This code would actually be embedded in a servlet or even an application. You can embed it anywhere. The first line creates a log4j logger, and then we create an event object, which we set the ID, timestamp, and source on, and then we can send that to the logger, which will actually send it to Flume. And the way that works is revealed by the log4j configuration that we're using. We're using a log4j appender that is Flume aware, but also CDK dataset aware, which means we have to tell it about the Flume agent, the hostname and port. Remember I said that the Flume agent would typically be running on the same node as the web server. And once Flume received the event, it would send it to the next tier, which would then send it to HDFS. And we also have to configure the the dataset name, so that Flume knows which dataset to write it to. So with all that code, we can start it running, and what we'll see if we look on the HDFS file system is files start appearing, because Flume will start writing files as soon as the events start streaming in. And they're Avro files, and this is what we would see over time. They would more and more would be created. So the next step was the creating reports. If you remember the diagram, we wanted to create hourly reports. So we're going to use Crunch to do that, and this slide summarizes the kind of core part of the code that you would write to get Crunch to generate these things. So this just gives you a flavor of some of the ideas in Crunch. And the first idea is of a P collection. That's the central type in Crunch. And it's a bit like a Java util collection, except it's not materialized. If you think about it, we're dealing with very large data sets here. You know, events could be a terabyte of data. You don't want to materialize that. Clearly, you can't do that in memory. So this is a reference to the data for Crunch to work on. So the first line is simply taking the data set that we defined earlier, which was called events, loading it and then converting it into a format into a form that Crunch can understand. Crunch operates on sources and targets, so we have to convert our data set, expose our data set as a source in this case. And the read command, the read method there, is something that Crunch exposes to take a source and turn it into a P collection. And notice that the P collection is parameterized by the POJO that we had earlier. So everything's written in the Java, idiomatic Java that we would expect to process these things. What we want to do, of course, is convert this P collection of events into a P collection of summaries. We want to do a transformation on it. So the middle block of code here does exactly that. And what we do is use some of the primitives in Crunch to do that transformation. Crunch has things like grouping. So you can see the by and group by key methods here to do grouping. And it also has parallel operations, which is the parallel do method here. And in some ways, these are reminiscent of MapReduce, but they're at a higher level. We don't have to worry about particular keys and values in the way that we do with MapReduce. So just very briefly, the grouping is grouping by the minute of the day and the source, because we want to do, this summary is just going to do bucketing by the minute of day. And we want to count the number per source for each minute of the day. So this code will do that. There are two mapping functions: getTimeBucket, which does a mapping between the event and the bucket key, and parallelDo takes a makeSummary mapping, which will take a list of the events that correspond to that key and turn it into a summary of whatever kind. Maybe we just want to count the number in that case. But you can do arbitrary processing in those functions. And once we've got the P collection of summary, we can write those summaries out to HDFS, to our data set. So we're converting our summaries data set into a Crunch target on the last line there. So this is much shorter than an equivalent MapReduce job as well. And it's pretty easy to run as well using some of the CDK tools. First of all, we create a summaries dataset. So we have an events dataset and a summaries dataset now. And then in the middle, we've got a snippet of a Maven POM, which specifies the tool class that we want to run when we run the CDK run tool command. And what run tool will do is execute that job for us. it'll launch it from our local machine and run it on the cluster. And Crunch will turn that into MapReduce jobs, actually. So one of the last things we're going to do now is query it with Impala. Everything so far has been Java. Impala is SQL, so we can use the Impala shell to issue SQL queries against the datasets. Here we're going to look at the events dataset, and we're just doing a describe here. And this shows that it can see it as a in relational schema form. So you'll see that there's big int rather than long, and that's because it's a relational form. And the comment is just showing that it's from Avro, actually. That's not very important. And then you can issue ad hoc queries, of course. You can run a select statement against it. This just counts the number of events grouped by source. This is a fairly small data set, but obviously it's just a few rows. But the Impala will run very efficiently against very large data sets as well. There's integration with JDBC, both for Hive and Impala. You can use the same Hive driver, actually, same JDBC Hive driver against both Hive and Impala. The JDBC URL varies. In this case, we're using an Impala URL. And it's very nice because Impala's low latency, so you can get very quick results, and so you can embed these things in web pages or do anything via JDBC that you would normally do. Okay, so that kind of summarized the way that you would write the code for the pipeline and use case that I showed before. I'm just going to go through some of the extensions, the other things that you can do with the CDK, and some of the stuff that we're planning in the future as well, I'm working on now. So when we ran the Crunch job, we actually ran, what you would do is you would launch it from your workstation. So part of it would be launched or run from your workstation, and a part would be run on the cluster. If you're running things in production, you really want to run everything on the cluster. You don't want to you don't want to have your workstation as a part of the production pipeline. So you need to package things as an app and then ship those to the cluster. And this is where Uzi comes in. There's a CDK command that will package your app, a bit like an exploded war for servlets. So it's actually an Uzi format, which means that it will have a lib directory with all of the jars, and then there'll be some configuration at the top level. And once you've packaged that app, you want to deploy it to HDFS. There's another command for that. And then once it's on HDFS, you can run it on the cluster. And you can just call CDK run app, and that will do a REST call to the cluster, and then Uzi will take over and run everything for you on the cluster. There are two types of app. There's a workflow app, which will just run things once, and there's also a coordinator app, which will run things repeatedly. And it runs other apps. So you deploy a coordinator app that runs a workflow app. And this works really well with partitions. So if you think of the example we just went through, the coordinator app would generate new partition data every hour or however often it was generated. Schema Evolution is a really important thing, and it's been built into this system. So if you wanted to add a new field, for example, to your event, then you can do so. And the tools make sure that only valid migrations are allowed. So if we hadn't made this new field nullable, then the update dataset command would actually fail, and that's because we need to make sure that the current schema can read old data. So remember at the beginning I said that it's schema on read, so we don't, if we update a data set, we don't go and rewrite all of the old data. I mean, we could do that, but it would be very expensive for big data sets. So instead, we have Schema Evolution where we make sure we can read the old data, and that's normally possible in practice, actually. So the trick here is that we state that the new field is nullable, which means when we try and read the old data with the new schema, the IP address field, the new field, will be null, which is kind of what you would expect. But the tools are a safety net, and they make sure that you don't do changes that the schema evolution rules don't support. Another really important feature is making datasets searchable. I said earlier that Solr is supported in the platform. So how would we make these datasets searchable? Well, as well as sending the events to HDFS, we'd want to index them on the way into the system. So we actually have another sink in Flume, which is called a Solr sink. And it goes to both the Solr sink, and events will go to both the Solr sink and the HDFS sink. And this is where we use the morphlines library that I mentioned before, and that would define the fields to index. And I've got a snippet of code on the next page to show that. And once the fields have been indexed, then Solr Cloud will actually run on the cluster and serve its indexes from HDFS. So if you've got you can use any Solr APIs at that point, so SolarJ or anything that Solr exposes, because it's just a regular Solr cluster, Solr Cloud cluster. And this is an example of morphlines. It's written in Hocon, which is the human readable JSON format. And we've only defined one morphline in here with ID morphline 1. The important part is the list of commands. We have a readline command, a grok command, and a load Solr command. Readline will read the next record. And in the example input here, we've got a syslog line. The grok command will do pattern matching. And in this case, I mean, there's quite a complicated expression there, but it allows pretty simple, each part is pretty simple. It allows you to pull out, for example, the first field is a priority field, the 164 in angled brackets. And we've pulled that out using the posint grok pattern matching. And that will stuff it into a field called syslog_pri, and that will form a part of the output record that's sent to Solr. So the output record is like a Lucene document that's sent to Solr. The morphlines provides lots of different commands that you can compose like this, and it's very flexible for pulling out fields and doing indexing. So I mentioned HBase briefly. We're actually working on HBase Storage. So you could have data sets that use HBase as the underlying storage mechanism. The only difference would be that you would have a different URL to access them, and then because HBase supports random accesses, then there's a different interface for accessing records. You can put or get records using this dataset access class. And the nice thing here is that some read patterns are best served by HBase. For example, if you want to do, if you've got a user data set and you want to mutate the user data, then HBase is an excellent choice. But if you're doing long streaming reads, then HDFS is much better. And the nice thing is if you've got a common kind of access through, a common abstraction through this dataset abstraction, then you can combine the two. You could use HBase for recent data and HDFS for older data, and you can compose the two dataset views so that you can combine those two to have access to recent data but also older data through the same API. As I said, we're still working on this. It hasn't been released yet. That concludes the slides. I can take questions now. Thank you. There's a question over here.
So you can do SQL queries with Impala, but also with Hive. What kind of queries would you prefer doing with Impala opposed to Hive?
The question is, you can do SQL queries with Impala, but also with Hive. When would you prefer one over the other? That's a great question. The Impala, as I said, is very good for low latency queries where you're trying to understand the data set, and maybe the amount of data that's returning will be very small because it's coming back to you, the user, on one machine. So you're doing summaries, basically. Hive is excellent for doing transforms. So if you've got some data and you want to transform it, like ETL, you want to transform it on the cluster into a new data set, you would use Hive because that's more of a batch process. The other thing about Impala is it has very short query time, but it doesn't have fault tolerance built in. So if one of the nodes fails while you're running, then your query will fail. The upside is it only took a few seconds anyway, so you can just reissue it and it's fine. But Hive, of course, is a batch thing and uses MapReduce, so it's fault tolerant. So if you've got a long running job, then you want to use Hive on that.
So there's no support in Impala for aggregations?
There is support in Impala for aggregations. There definitely is, yeah. Yeah.
It sounds like it's possible with Impala, but just for small ad hoc queries.
Yeah, for small ad hoc queries, exactly. Any more questions? At the front?
When you add a new dataset, do you have to do something at the Hive or on the Impala?
When you add new data sets, do you have to do something in Hive or Impala? No. So that's taken care of by this abstraction. The slide where I created a data set in Java, that created it for Hive and Impala as well. So the idea is that it's centralizing the definition of the data set for you, and it's making sure that it works from different engines, so it's working from Impala as well. Yeah.
Normally, I used Impala before just for test purposes. For example, if I add something on the Hive schema, I used MySQL for storing the schema. I had to refresh on the Impala side to get the exact schema. So there's nothing like that.
Right, so the question is, do you have to refresh the schema in Impala? You do, actually, yes. That's a refresh. That's not actually saying this is what it is. You just have to refresh the metastore. That's a synchronization thing. I think that's going to be, that improvement is coming, so you don't have to do the refresh. Any more questions? No, I don't think so. Great. Thank you very much.